Hello, welcome to my presentation about eye diagram testing. I would like to show you today a way how to get quicker to your results. My name is Guido Schulze. I'm a product manager for oscilloscopes at Rohde & Schwarz. Let's have a look to my planned agenda for today. As an introduction and as a kind of warm-up, we together will review typical challenges of high-speed interfaces and respective approaches for signal integrity analysis. Of course, I would like to focus on eye measurements today, so we start to discuss some basics about eye diagrams. Then I will review together with you some traditional eye analysis approaches before I then get to my main part to introduce to you a new approach where we use a hardware clock data recovery. In the following then, I would like to show you how to get from a very quick approach to the very details of a measurement, and I will finish with some quick summary. Let's start from a very high level. If we look to modern electronic designs, they very often include high-speed interfaces such as USB, PCI Express, MIPI, Ethernet, DDR, to name just a few. And the problem is that the data rate is really increasing here, and this gives us some signal integrity challenges. And the second challenge really is that we have more and more components combined on one design, so there's also the likelihood of interference from one IP block to the next. So this means I need some good solutions for signal integrity analysis, and I need test and measurement equipment that collects data fast so that I have a good basis for statistical analysis. Here I have a list of potential items what can go wrong on a design. If you look to my little example here on the right side, I have a transmitter connected to a PCB board. Then I have vias, I have a signal trace on the PCB board, I have vias again, I have a connector to another board, and so on. So until my signal reached the receiver, there are potential issues for signal integrity. So one category are channel-related effects. So there could be, or there will be some signal loss, some attenuation due to the traces, due to the connectors. There will be reflections due to impedance mismatch. But also there are, of course, original issues from the transmitter, like rise fall time imbalance, some timing jitter, some noise. But also, like I mentioned, devices are getting more and more complex. You have several sources of signals there, so external sources could really interfere my transmission from my signal from the transmitter to the receiver. So what are the dedicated tools that we can use for testing and for debugging? So first of all, it's about the eye diagram. It's a, let's say, very quick way to look to the signal integrity. I overlay signal bits over each other, and then I get an intuitive way to look to noise and to jitter. A second then step would be to try to analyze in detail what are the sources of my noise and my jitter, and therefore you might use then also an advanced jitter and noise analysis where you break down the individual jitter and noise components, and then you can conclude on potential error sources. And last but not least, I also would like to mention compliance testing. So if I have an interface like USB, I also might want to do some compliance testing towards the standard. Is my signal compliant to the standard? But for today, I would like to focus on eye diagram analysis. So let's start with some basics. First of all, an eye diagram, as I mentioned, is a very intuitive tool to look to the quality of the transmission of my signal. And the way the eye diagram is generated is that I look to my signal stream, and I need to find some way to slice the individual bits. So I need some timing information, either a separate clock signal or an constructed embedded clock signal, to have really an isolation of my individual bits, and all the individual bits then they are overlaid to each other so that I get an eye diagram like you see it here in the middle of the picture. So as I mentioned, it's very important that I have a good timing reference. And for example, for parallel interfaces like DDR, I have a data signal, I have a separate clock signal. So we talk here about a parallel interface. So I use the timing edges of my clock signal to slice my data stream into individual bits. But for many interfaces like USB, PCI Express, and so on, we have embedded clock signal. So I include into my data stream here from my transmitter and clock into the signal. And on the receiver side, I need a clock data recovery in order to extract the clock signal and in order to do then the bit slicing again. So the clock data recovery, typically it is based off a phase lock loop or a delay lock loop, so a PLL or a DLL. This means if I now with a test and measurement equipment, I want to test some signal here, I need to have a kind of clock data recovery in order to see the signal with the timing information of the signal itself. So if we now have been able to reconstruct my data eye, then I have a lot of possibilities to analyze the data eye. You see here in the middle, for example, there's a mast. So we need an open area where the receiver can safely distinguish between a 1 or a 0. So I want to extract the logic information. I can look to the jitter on the crossing of my rising and falling edges. I can look to the noise on my amplitudes. And very important, I want to look to how wide is my eye open in terms of timing and in terms of amplitude. So these are the key information that I can get out of my data eye. Let's have a look, first of all, what are the traditional approaches? And basically, we distinguish two different areas or two applications for data eye analysis. First of all, I take just every then and a while a single bit that I monitor. So I acquire one bit here, another bit here, another bit here, and I overlay them by using an edge trigger where I use the rise and falling edge, and out of this I get a data eye. So this is very useful, for example, for long-term monitoring for interference detection. The second approach would be to use an, let's say, continuous bit sequence. And here, then I apply the discussed clock data recovery. So basically, this is a clock data recovery in software implemented. So I do this in post-processing. And this gives me the timing information to do the bit slicing in order to get the data I like displayed here on the top of the slide. And here the typical application is that I do a characterization of my transmitter output and its signal path itself. So if I compare these two approaches, I see the two different applications. One is the monitoring of my signal to detect some interferer. The other is to do rather the characterization of my transmitter and the signal path. So for the single bit approach, it's very easy. I use my edge trigger, very easy setup. But on the other hand, with the edge trigger, I don't get all the information. I don't get all the jitter information. I only can capture transitions and so on. If I use the clock data recovery, then of course the setup is more complex, but I get more information, but also I need a long processing time. So what is the new approach that I want to present to you? Today, in our oscilloscopes, the RTP oscilloscope, we have implemented in the trigger circuitry and clock data recovery. So it's a hardware-based clock data recovery. It can log on the data stream. So it logs once and then it is continuously running. And based on this CDR timing information, we can then build the data eye. So if we look to our trigger circuitry, we have a new type there. It's called CDR, and this CDR is programmable. So I can program the nominal bit rate between 21 kilobit per second up to 16 gigabit. So this is industry unique, but I also can program the tracking bandwidth. And in order to make it for the users easy, we have some predefined settings, so depending on the standard that you use. So with this approach, with having this hardware CDR, we now can do the two algorithm again. So I take a short record length or a short acquisition, and I use the CDR timing information, and our oscilloscope has a really fast acquisition rate, so I can capture or I can acquire a lot of bit pieces and overlay them over each other within persistent mode, and I can monitor my data signal for hours, waiting for some interference that I can capture with my mask. So this would be the first application. I do a long-term monitoring. I just look for my individual bits, and I do a long-term monitoring looking for interference. The second was acquiring a long data sequence, so for example, 200 microseconds, and then applying the timing information from the CDR. So for our trigger system, we use this hardware-based CDR. We can, beside the saving the waveform, we also can save the timing information from the CDR, and we use this then for the bit slicing. So all the individual bits then are overlaid in this eye diagram here. And with this, we can characterize the transmitter and the signal path. And again, the tools that we can use are mask tests, histograms, and so on. So how does it then look on the machine itself, on the oscilloscope? I select under my application tools the eye diagram. I configure my hardware CDR. So in the easiest way, I just define what standard I use, and then I say just switch on, and I get my eye diagram. So just 3 simple steps in order to get to an eye diagram. And then in the following, I have plenty of possibilities to improve my settings and to get really to a debug mode. I have different options for the display. I can choose between different color tables, between different persistence modes. I have a very powerful function which is called EyeStripe. I give more details about this in a second. I can define a gate on my signal, and I can also apply filters, like I want to have all bits included in my eye diagram, or I just want to look for level transitions. So if I have a transition from 1 to 1, when there's no transition, this is not excluded. Or I just want to have a data I build of constant levels. So here a 0-0 transition or 1-1 transition. Or I have a dedicated pattern in mind where I just want to look to data bits that are after this dedicated pattern. So also this I can program. And so I can really focus my analysis there. A very powerful tool in combination with the mask is the so-called EyeStripe test. So if I have a mask test defined in my eye diagram and I have a violation, like you can see here in this area, so there's a small violation, then I get in a list of failures, and these failures I can map to my acquired waveform. So you see here the little stripes, the little red dots. So these are the EyeStripes. And with this table here, I just tip on one of the violations, and then my zoom window jumps immediately to the respective errors in my waveform stream. So for example, here in my zoom, now I'm focused on the error number 11. And I see here in this area, this is causing my violation of my eye diagram here. And so I can do a correlation between my masked failures versus the timing where it happens. And maybe there's some other signals also connected to the oscilloscope. So maybe there was another spike, another interferer, another problem. So I can do a time correlated analysis there. Also very important, if I have my eye diagram, I want to apply measurements. I want to apply measurements like eye height, eye width, and that's why we have a long list of predefined automated measurements. You see here a long list where the measurements are applied. I have special parameters that I can use for configuring the measurements. So, for example, my eye width is related to my 60% and my 80%. So my width starts just from here, and then I measure in this direction. So I have a lot of configuration possibilities there. This was just a brief overview to the eye measurements and how you can do this with the Rohde & Schwarz oscilloscopes where you use the hardware CDR. Once I have an idea about my signal integrity in the eye diagram, I also can now do the next step where I use advanced jitter analysis and where I want to break down the individual jitter components. So in the eye diagram, I mainly see the total jitter or the total noise, which is then depending out of different components, deterministic components, jitter, random components. And if I now, for example, there is a periodic jitter with a certain frequency, then I can also conclude on my design what to improve. So also such capability are possible with the Rohde & Schwarz oscilloscopes. You just see here some example where some measurements were done. You see histograms of individual jitter components, but you see then also the correlation to the eye diagram again. So let's come to the summary. So traditional eye measurements, they have different approaches that are typically used. One is for long-term monitoring. They use an edge trigger, for example, and you look to individual bits. So you have a short acquisition range. You look to individual bits for a very long time because you want to detect some interferer. And the second approach is to look to one dedicated signal stream of continuous bits. Then you apply a clock data recovery and you look for the details for the characteristic of the transmitter and the signal path. With this presentation today, I wanted to show you a new approach where Rohde & Schwarz has implemented a hardware clock data recovery in the trigger circuitry. So it's very much integrated. You can use this on all 4 channels of the oscilloscope, and this enables the true eye diagram measurement where I look for signal bits. We call this now real-time eye because we acquire the data very, very fast. Or the other approach would be that you also can use the hardware CDR to do the bit slicing of a continuous bit stream, and you just use the timing information of the clock data recovery. Because the Rohde & Schwarz oscilloscope acquires waveforms very, very fast, we can collect data very, very fast, and you have a high statistical confidence. And I also showed you with the additional tools of the advanced eye option, you can then apply automated measurements, you can apply mask tests, histogram tests, etc., in order to get more details about your device. And last but not least, then there are additional tools to look more into the details of the jitter and the noise with dedicated jitter noise analysis, where you break down the individual jitter and noise components. With this, I'm at the end of my presentation. Thank you very much for your attention, and please, if you have questions, there's time for questions now. Thank you very much.